Good morning, everybody. Welcome to your intro lab to Lab 7, which is habitable zones. This will tell us all about habitable planets, how they work, how they change, how they relate to this star. I thought it'd be fun to do a screen video for you this morning so you can actually see the simulator work instead of just having me talk about it. And this top panel here that we're looking at, I hope, is showing you the actual star, and over here is the habitable zone, and here's a planet that's in the habitable zone. Notice that the orbit locations of Mercury, Venus, Earth, Mars, and the other planets are shown, even if those planets are not there. That gives you nice markers. You know that the Earth is at 1.0 AUs. Venus is about 0.7, Mercury is about 0.4, Mars is about 1.5. So it helps you see where you are in the solar system. Now, what's interesting here is that the habitable zone is basically defined as the place where liquid water is stable on a planetary surface. That's taken as the most important condition for any type of life at all. So that's how this ball game is played. Now notice I can move this little puppy around. And if you were watching, watch what happens when I take it out of the habitable zone. It changes color. How convenient. And what's happening is it's going from a blue state, because it has liquid water in the habitable zone, to a sort of brown state because the water is presumed to be gone or going at that time. And if I bring it in even further, let's see what happens. Up, there it happened. Let's bring it back out so you can see the transition. There it is. Now watch what happens if I'm careful with this. It will do that. And notice what the planet is showing you there. It has a vertical dashed line through the center. That's telling you that the planet is tidally locked, and that happens when planets get too close to their stars. They end up locked with one face towards the star and one face always against the star. This is synchronous rotation. It's exactly what our moon does with the Earth. The moon is locked in that same sort of tidal locking. The moon always has one face toward the Earth. But for a planet that has one face toward a star, that generally means, unless you have a thick atmosphere that's moving heat around other ways or an ocean, that generally means that the side towards the star is hot and dry and the side away is cold and frozen. But we'll just, and notice that only happens when you get close, because now it's gone. I moved it just back out. So if we bring this back out, notice, oops, notice it changed color. We're back to the blue again. And now we can, whoops, got carried away here. Notice on the other edge, on the outer edge of the CHZ, which is the Circumstellar Habitable Zone, or just the Habitable Zone, or the CHZ, notice that it has a white sheen to it, which means things are frozen. So we can move it in and out. I can put it anywhere I want. So that's the kind of thing that you can do with the top panel. Now, over here on the general settings thing, basically it's a good idea to keep the solar system orbits on, even if you're not in the solar system anymore, just so you know roughly where you are. See this little initial star mass thing? I can control that anywhere I want. Notice what happened. I don't know if you saw that. It happened pretty fast. For a star of 1.0 solar masses, these are the masses of the sun, the Earth at the beginning of history for the solar system was right in the middle of the CHZ. But as we move the mass up, it's up at 1.2. Notice the CHZ is migrating outward in the solar system, basically leaving the Earth behind, because the Earth stays at 1 AU, okay, with certain exceptions. And the reason the CHZ is moving outward is because of these little numbers right here. Notice when the mass goes up, guess what? So does the luminosity. Luminosity is the energy per second coming off the star. So, in other words, to stay cool enough to keep liquid water, the CHZ has to migrate out of the outer solar system. And notice the radius also gets bigger for a bigger star. And so that's an interesting thing you can notice as we go along. These little numbers are very important here. So is this one? This tells you the planet's distance now in AUs. If you're ever curious about that, you can actually see it anytime. Over here, there's a neat little menu that'll give you your choice of 6 specific stars, or you can leave it in the none selected, and you can manipulate the mass any way you want. But if you choose one of these, like 51 Pegasi, it automatically puts you in 51 Pegasi. What you should do when you go to a new star is check to see what you're dealing with here. Here's mass is 1.1. This is the real mass of 51 Pegasi. It's no fictional thing. This is the real luminosity, about 17% larger than the sun's. It's a little warmer, and notice the radius is just slightly bigger. And it has a planet called Planet B. And notice this just all came up when we brought up 51 Pegasi. The planet is already tidally locked here, and the planet, of course, is at 0.05 AUs, 5% of an AU. We're not surprised at that close a distance that it would be. So let's go on back, and we can do this with the other 6 stars if we wanted to. Let's put it back on none selected, and we'll go back to sun numbers, which is 1.0. And we'll take this planet, put it back in the CHZ. It'll come, there it is right there. By the way, if you want to go to the outer solar system, you can do so, but you have to hold down the cursor and then just drag out like this. And then you have to hold it down to keep it there. If I let up, that's what happens. It goes back. You can do it the other direction too. Now, the one thing we haven't talked about is the timeline and simulation controls. And this is already getting to be a long video, but that's okay. This is fun to watch. Notice there's a little arrow here that starts at time 0, and it goes as far as you want over here in time. And everything changes when you let the star evolve, because we're starting at time 0 for the star, and in this case it's the sun and the earth. So as we move this to the right, notice what's happening to the CHZ. Are you watching? The CHZ is migrating outward. This thing is moving outward in the outer solar system because the sun's luminosity is actually increasing. Let's go back and look at the numbers here again, just for fun. Notice that at the sun birth, when it first got on the main sequence, it only had a luminosity of 0.74 of its current luminosity. So the sun was born a lot dimmer than it is today. It's actually been getting brighter throughout its main sequence lifetime. And we can actually, if you watch that luminosity grow as time goes, that's why the CHZ is migrating outward. This is all realistically done. Very clever little thing. Now here, let's go out to 4.6. We just passed it. How can we tell we're at 416? Because it says the time since star system formation. So 4.6 is the age of the sun and the earth. So this is the way things actually are. You're looking at a realistic simulation of what we actually see. Notice that the mass of the sun is 1, of course. The luminosity is 1.02. That's much higher than it was 4.6 billion years ago. And the radius is almost normal right now. But notice where we are in the CHZ. We're on the inner, not quite the inner edge, but we're moving toward it. And one of the interesting questions is, take this out to the point where the planet leaves the sea, there, right about there. And so that's the time between where we were and where this is given down here. The time right now is 5.46 giga-years. That's a billion years. So if we subtract 5.46, if we subtract 4.6 from 5.46, we'll get something a little bit less than a billion years. That means we have maybe 800 to 900 million years left of the Earth actually being in the habitable zone. And that's accurate because we do expect Earth's oceans to be triggered in about that time frame. So it's very interesting to see this little guy actually doing this. Now, on page 2, it asks you to do all sorts of interesting things, including manipulate the star mass. Let's go ahead and take it down. We'll look at 0.7 just for fun, and you can do that by using this control. There it is. That's 0.7. Notice that here at 1 AU, if we had a star of 0.7 mass, the Earth would be way, way out on the cold side of the habitable zone. Anyway, if you want to know where the habitable zone is, that's easy. Just put the planet there and then read off down here the planetary distance. Now that's 0.506 AUs, and the inner side is, whoops, is right there, 0.350. If you subtract those two numbers, you get the width of the habitable zone, which is one of the questions they ask you. And of course, we set the luminosity. So we could set the luminosity for any star and easily measure the width of the habitable zone. And that's one of the things they have you do here. And that's very revealing in terms of what kind of stars have what kind of habitable zones. I showed you how to do the 51 Pegasi thing, and the time evolution thing is over on page 4, and I'm looking at it now. Just to give you a little more details about this, this is actually telling you down here when the star becomes a white dwarf. Remember, the star becomes a white dwarf after it goes through its red giant phases. And here it says star stops fusing H. That's when it runs out of them. So let me show you real quickly. Let's see, let's take it back to 1 solar mass so you can see what the sun does. There it is. We'll move the Earth back into its comfort zone. And this is about where it started. So now if we run this, watch everything. In fact, let's do an automated run here just for fun. We're going to have to move the rate back so you can actually see it. Watch everything. This is notice the CHZ is migrating outward. Notice the sun's getting older. Notice we're very close to 4.6. There it is. Boy, that was good. I stopped it right on it. But notice the sun has a long way to go in terms of burning hydrogen. On the other hand, we know that the Earth only has about 800 million years left in the CHZ. Let's keep on running it. And it's moving now towards the second half of its life. I mean, the sun is. Why is the CHZ migrating outward? It's because the luminosity is getting big. Look at this, 1.5 solar luminosities, and this is 8.15 billion years into the sun's life, okay? Let's keep going here. And the sun's getting older and older and older. Now notice, boom, there's where the sun, if you look down at the bottom here, the sun has just stopped burning hydrogen because it ran out, okay? And what that means is that it's about to become a red giant. Let's see what that looks like. Yes, it's happening. Notice the CHZ has left the picture, although we could drag it in if we really wanted to. Watch the star, it's getting bigger. Are you watching over here? We're actually simulating the sun's life. There's a red giant phase right there. Notice the luminosity is 140 solar luminosities. The radius is already 22 times the current radius, so it's definitely getting big. Oops, it just flashed at us and became, let's see if I can bring that back so you can actually see it better. We'll make it very slow. That's as slow as I can run it. And now it's already 42 solar radii. So this is what happens, and it continues on and goes through another red giant stage. Let's speed it up here a little bit. And it did it again. And now it's at white dwarf land. So let's look down here at radius, 0.01, 1% of the sun's radius. That means it's a white dwarf. Notice the luminosity is very low. Notice how the habitable zone has collapsed in onto the star since it's not giving off much light. So this is the kind of stuff you can do with this. And I think that's basically it. Everything is just about like that. And we're 14 minutes into this video. So I'm going to stop it there and look forward to your questions if you have any.